Scattered across our remarkable planet hidden just beneath the surface, lies a group of extraordinary elements. These are the rare earth metals. There are 17 of them in total, with names that sound like they belong in a book of ancient spells: neodymium, lanthanum, cerium, yttrium. Despite their name, they are not always exceptionally rare in the Earth's crust. Some are actually more abundant than gold or silver. Their true rarity comes from the fact that they are seldom found in concentrations high enough to make mining them a simple task. They are the shy, elusive members of the periodic table, preferring to remain dispersed and unseen, waiting patiently for discovery. These metals are the secret ingredients that power our modern lives, the unsung heroes behind the screens and circuits that connect us all. The vibrant colors on your smartphone screen, the powerful magnets inside the wind turbines that generate clean energy, the tiny, precise motors in a hospital's MRI machine, all depend on these special elements. They possess unique magnetic and conductive properties that no other material can replicate. Without them, the technological leaps we have made in recent decades would have been simply impossible. The search for rare earth metals is a journey into some of the planet's most dramatic and ancient landscapes. These elements are not found just anywhere. They are concentrated by immense geological forces over millions of years. Towering mountain ranges born from the colossal collision of tectonic plates are prime locations. As mountains are pushed upwards, deep-seated rocks rich in these elements are brought closer to the surface. The immense pressure and heat involved in mountain building can create specific igneous rocks, carbonatites, granites. Here, in the planet's great wrinkles, geologists begin their search for telltale signs of these valuable deposits. Ancient volcanoes, long since silenced, are another key hunting ground. When these fiery mountains were active, they acted as elevators, bringing molten rock, magma, up from deep within the Earth's mantle. As the magma cooled and solidified, these elements crystallized into distinct mineral formations. Vast, arid deserts also hold surprising potential. Erosion can break down host rocks and sometimes concentrate heavier, more durable, rare earth minerals. The dry conditions preserve these deposits, preventing them from washing away. Finally, we turn to the patient work of rivers. That process liberates minerals and carries them downstream. Denser rare earth minerals tend to settle in specific spots, like inside bends of a river, or in ancient riverbeds, placer deposits. Prospectors look for unusual discolorations in the soil and mineral veins snaking through exposed rock. Over time, these spots can become incredibly rich. It is a slow, natural sorting process where water gathers and concentrates what the mountains have offered up. These clues lead us from landscape to lab. Next, how geologists turn those clues into discoveries. The quest for rare earth metals begins not with a shovel, but with a map. Geologists and prospectors first study geological surveys and satellite imagery. They look for the right kinds of rock formations and for areas with a history of volcanic activity. Specific igneous rocks like carbonatites are promising hosts for rare earths. This stage is detective work on a grand scale, piecing together clues from the Earth's distant past. They search for patterns, anomalies, and geological stories that hint at hidden concentrations below the surface. Once a promising area is identified, the real fieldwork begins. Scientists venture into remote, rugged terrain with specialized tools. Key instruments include a scintillometer and a portable spectrometer, used to detect faint signatures. Teams walk the ground systematically, taking readings and collecting labeled rock samples. It's a slow, meticulous process requiring patience and a keen eye. Samples are sent to labs for thorough analysis. Techniques like X-ray fluorescence and mass spectrometry reveal exact chemical compositions. This is the moment of truth, confirming presence and quantities of rare earths. Finding a trace is one thing, finding an economically viable concentration is another. Lab results guide the decision to move to the next stage. If results are encouraging, the final step is drilling. Small targeted holes extract core samples that show a cross-section of the geology. These long cylinders reveal depth, thickness, and richness of the ore body. Drilling is the most expensive, definitive phase, confirming size and quality. Only then can a company decide to establish a mine and begin extracting these vital components. From lab to site, the path is long but precise. These discoveries power the devices we rely on every day. For many decades, the story of rare earth mining has been overwhelmingly dominated by one country, China. The Bayan Obo mine, located in Inner Mongolia, is a place of legendary scale and significance. It's the single largest source of rare earth metals on the entire planet. The geology here is unique: massive carbonatite deposits and integrated processing infrastructure. This concentration of geology and industry made China the undisputed leader in mining and processing. However, as demand has grown, exploration has expanded around the globe. In the United States, the Mountain Pass mine in California stands as a symbol of renewal. Once the world's leading producer, it faced closure and later revitalization. Now it's being brought back into operation to diversify global supply. Across the Indian Ocean, Western Australia is a major player. The Mount Weld mine is a different style of deposit, weathered carbonatite with very high concentrations. Australia has invested heavily in mining and processing capabilities. Exploration projects are active in Canada, Greenland, Brazil, Vietnam, and parts of Africa. Each location presents unique challenges, from harsh Arctic climates to complex logistics in remote jungles. The quest is truly global, and diversification is vital for secure supply. This diversification ensures supply can keep pace with demand for greener technologies. It supports the global transition to EVs, wind, and high-tech manufacturing. Exploration and investment around the world are accelerating. From China to Australia and beyond, the search continues. Next, why this matters for our future. The continued discovery and responsible extraction of rare earth metals are absolutely fundamental to shaping the future of our civilization. As we move away from fossil fuels toward cleaner alternatives, these elements become more critical than ever. The powerful magnets made from neodymium, dysprosium, are the beating heart of high-efficiency generators and compact EV motors. Without a secure supply, ambitious goals for combating climate change would be difficult to meet. These components underpin the green infrastructure we rely on, and the advancement of technology in nearly every field depends on rare earths. In medicine, gadolinium is used in MRI contrast agents. In communications, erbium amplifies signals in fiber optic cables, enabling the high-speed global internet that connects us all. This great search also presents us with a profound responsibility. Mining can have significant environmental impacts if mismanaged. The challenge is to develop cleaner, more efficient techniques and to restore landscapes. Improving recycling methods to recover rare earths from old electronics reduces reliance on new mining. Acquiring these materials must honor our role as custodians of the planet. Our ingenuity must be applied not only to using these materials, but to acquiring and recycling them responsibly. Ultimately, the story of rare earth metals is a story about our own future. These hidden elements forged in the earth over geological time are now key ingredients in the world we are building for generations to come. From the smartphones in our pockets, to the vast renewable energy projects that will power our cities, their influence is everywhere. The search for these treasures will determine the pace of human progress.